Hello everyone, we are gonna talk about our paper, Depth Estimation from a Lightweight ToF Sensor and RGB Image. Depth sensors is essential for a variety of applications such as augmented reality and robotics. For example, a series of interesting motion sensing games on Xbox are based on Microsoft's Kinect depth camera. Also, more and more smartphones integrate depth sensors for better interaction, augmented reality applications and so on. Currently, there are three main technologies for depth sensing. Among them, time-off flight-based sensors are compact and have become one of the most popular classes in the depth sensor market, especially for smartphone. However, the price and power consumption of them, though already lower than other technologies, are still high, say, at least 1 to 2 orders of magnitudes higher than a typical RGB camera. On the other hand, lightweight ToF sensors are designed to be low-cost, small, and low-energy, which have been massively deployed on mobile devices for the purposes like autofocus, obstacle detection. But due to the lightweight electronic design, the depth measured by these sensors has more uncertainty and low spatial resolution. For example, L5 is a lightweight ToF-based depth sensor. They provide resolution of 8x8 zones, covering 63-degree diagonal FOV in total. As a result, each zone corresponds to a not-so-small area. L5 measured depth distribution of these zones instead of a single depth value. Since the depth distribution contains rich information, a natural question to ask is, can we empower lightweight ToF sensors with the capability of measuring high resolution and accurate depth? Our answer is it can be done with the help of a RGB camera, which commonly coexists on mobile devices. As shown in the figure, we improve the depth quality of these low-cost and low-power consumed sensor to be on par with a commodity-level RGBD sensor by our DELTAR algorithm. The task is essentially different from previous depth super resolution and completion in terms of the input depth signal. In short, our task is novel and challenge due to the extremely low resolution of the input depth but accessibility to the rich depth distribution. To demonstrate, we build a device with hybrid sensors, which is shown in the figure. In order to align the L5 outputs with the color image, we need to calibrate this multi-sensor suite. Similar to the calibration between LiDAR and camera, we also calibrate our device suite by solving a point-to-plane fitting problem. However, it is not trivial to fit a plane with raw L5 signals since it does not provide the pixel position of the depth value. Therefore, we propose an M-like algorithm to optimize both the plane parameter and the pixel position. Our model are based on the commonly used U-Net architecture. It takes depth distributions and color image as input, and fuse them at multiple scale with attention-based module before predicting the final depth map. Our key design is twofold. We first design a module to extract features from the distribution, which is barely studied. A straightforward idea is to encode the mean and variance directly, which we show in the experiment that it do not work well. Therefore, we propose to build the depth hypothesis map sampled from the distribution reading of L5 and utilize PointNet to extract depth feature from these hypotheses. Secondly, we propose transformer-based fusion module. Previous fusion design concatenate or sum multiple module feature in the fusion step, which is not suitable for our task since pixel-wise alignment is not available between the depth hypothesis map and the RGB features. Instead, we adopt attention mechanisms, which learn to focus on subcomponents of the cross-modal information and retrieve useful information from each other. A self-attention is also run on image domain to exchange the information between regions covered by L5 and beyond, hence the output aligns with the RGB image and covers the whole FOV. Since the current datasets do not contain the L5 signals, we create an indoor depth dataset, called ZJUL5, to evaluate our method. For more details, please refer to our paper. This table summarizes the comparison between ours and other three types of methods. For all metrics, our method achieves the best performance among all methods, which indicates that our network customized with respect to the underlying physics of the L5 is effective in learning from the depth distribution. We also show the qualitative comparison. Our method produces the most accurate depths with sharp object boundaries. In the end, we show a short demo. The input color image and L5 signals are shown in the left column. According to the status returned by L5, we hide the invalid zones which may receive too few photons or are unstable. Although the raw signals from L5 have extremely low resolution, we can improve its quality and make it even on par with RealSense depth sensor, by fully exploiting the captured depth distribution and fusing with color images. Here is the link of our project. You can also scan the left QR code to visit our project page. Thank you for listening.